Welcome to all in exam race. This is the quantum mechanics and we are here for identical particles. So when we talk about the identical particles, we have two cases. One is in a classical and another is in a quantum mechanics. So classical, it is very easy to find the or easy to distinguish the two particles. Just mark them. Suppose we have two balls, mark one with 1 and another with 2. So you can easily distinguish the similar particles. But in classical, the particles are visible, but in quantum, the particles are not visible. So it is impossible to, sometimes it is impossible to distinguish the particles, because suppose two identical particles are there, same particles are there and they move. Suppose this is one, the move, and another, it is also move, and after that they superimpose. So after superimpose, it is impossible to distinguish the particle. Okay, so what we will do for this, consider two non-interacting particle in 3D. Okay, so its behavior by Schrödinger equation is like this: minus h cut square over 2m del of 1 2 minus h cut square over 2m del of 2 2 psi of t plus v of psi of t equals to e of psi of t. Okay, where m is what? The mass of particle. And if what is del 1 del 2? So this del 1 and del 2 are for coordinates, two different coordinates of particle. Okay, two different coordinates of particle. Fine, and these are two non-interacting. So its potential V, that must be equals to potential at one of the first particle at one coordinate and potential of particle at second coordinate. And for this, which we have solution, that is of psi of total solution. T is for the total solution, that is psi of x1 y1 z1 into psi of x2 y2 z2, and each either psi of x1 y1 z1 or psi of x2 y2 z2 requires the quantum numbers to specify the dependence in the 3D coordinate system. Okay, and one quantum number is different with the other quantum number in the spin state. Okay, how much the particle is identical, but there is a quantum state which may have some certain differences, and here it is shown by the quantum numbers. Means no two particle have same quantum numbers. Okay, so if no two particle have same quantum number, if all the particle suppose there is two particle, if all the quantum number are same in two particles, only the spin, either it is up or down, spin is the quantum number that the particle is not same. Okay, now let alpha and beta are the states of two electrons. Okay, thus we can say that psi of alpha for 1, okay, psi of alpha 1, which means that it has mean, which means that it has a wave function of particle 1 in a state alpha. Similarly, psi beta, if I write the beta 2, which means the wave function of particle 2 in state beta. Simple. So this is what the denotion of alpha 1 beta 2. Now psi of alpha 1 into psi of beta 2, these are the possible solutions, but we are not sure that are they distinguishable or are they same. Okay, so to measure their quantity is the simplest ways to measure the probability. So if I want to find the probability of total function, then it's going to be the psi a or not. Okay, psi alpha, it is psi alpha 1 into psi alpha 1. Okay, psi star alpha 1 psi is into psi alpha 1, and also psi beta 2 and psi beta. Simple. But still psi of t square is not best. Why it is not best? Because it does not remain unchanged. It does not change. Oh, sorry, it does. It may change. It does not remain unchanged. That means it may change for particle 1 to 2. Means there is exchanges possibilities are there. Changes are there. Possibilities of exchanges are there. So to avoid that, we must construct a linear combination. And what does it linear combination? Linear combination in such a way that it holds the Schrodinger equation, means it holds the solution for the Schrodinger equation. So I'll tell you like this. And one is S psi of S. I'll tell you what is psi of S. So it's psi of alpha 1. Up to now, in psi of t total probability, we see that it does not remain unchanged. Okay, but here you can change that. It remain. Do this. Okay, psi of alpha 1, it's beta, plus psi of alpha 2, psi of beta 1. Okay, and after normalization it is 1 by root. Now psi of a, it is psi of alpha 1, psi of beta 2 minus psi of alpha 2, psi of beta 1 over root 2. Now what is psi s and psi a? It is for symmetric function, and it is for anti-symmetric. Okay, anti-symmetric. These two functions remain unchanged for the eigenfunction of Schrodinger equation. Okay, this is to remain unchanged. But as we decided this, when we decided the probability function, that was not remain unchanged, but this remain unchanged.